from space. So, quick disclaimer, this talk is only 20 minutes, so I only have time to give you an intuition for how landing works. If you actually want to go fly the real shuttle, please make sure you read the owner's manual. Also, you're going to need a time machine because the last shuttle landed over 5 years ago. They all live in museums now. They're completely unflyable. However, I, like all of you, have been living in a state of denial for the last 5 years. Especially you, Steve Feldman. So in my world, the shuttle still flies, and we're just going to use present tense for this talk. All right, so let's get started. Our goal is to land on a runway at Kennedy Space Center in Florida. But let's say right now we're orbiting over South America, traveling over 17,000 miles in the wrong direction. Well, we can't just turn around. Changing direction in orbit takes crazy amounts of energy. So what do? Well, basically nothing. So it turns out that the Earth spins, which means that Kennedy Space Center is just going to come to us if we wait for it. So this time around, when we come up to Kennedy Space Center, we're just going to stop. It always does this. So it turns out that we're still traveling over 17,000 miles an hour. To give you some perspective of how fast that is, the runway that we're going to land on is 15,000 feet long. That's about 3 miles, or maybe 40 to 45 football fields, depending on what you consider a football field. It's one of the longest runways in the world, but at our current speed, we're going to travel the entire length of it in just 0.6 of a second. We could get from New York to London in just 12 minutes. So we need to slow down a lot. Well, the shuttle's got great engines, plenty of power to slow us down with. So let's just fire them up again. So this is kind of embarrassing. See, we're sort of out of gas. Womp womp. In our defense, launch is really expensive. Those 2 boosters on the side, they burn 1.1 million pounds, or 500,000 kilograms of solid fuel in just 2 minutes. And then we just throw them away. That big orange external tank holds another 1.6 million pounds, or 725,000 kilograms of liquid fuel for the shuttle's 3 main engines. But after an 8-minute launch, those are empty too, so we have to ditch it. Bye. All we got left are these wimpy little orbital maneuvering engines, which combined produce less than 1% the thrust of the main engines. They're not going to slow us down 17,000 miles an hour, but there's a trick. We don't actually have to slow down by that much. If we slow down by just 225 miles an hour, that's enough for us to start falling into the atmosphere, where air resistance can do the rest of the work. So we perform our deorbit burn, which lasts about 3 minutes with our orbital maneuvering engines. After that, we're just going to coast for about a half hour before we reach the atmosphere. But we can't go in the atmosphere backwards. First off, we would look ridiculous. But possibly more importantly, the air resistance is so great that we would essentially melt. So we pitch up to 40 degrees angle of attack. That's the angle between where your velocity is taking you versus where your nose is pointed. At this angle, our easily meltable aluminum airframe can be protected by over 20,000 silica tiles, as well as these reinforced carbon-carbon panels on the nose and the leading edge of the wings. Fun fact, the surfaces of the orbiter which don't get as hot are covered by these thermal blankets, as well as a Nomex felt fabric that goes over the wings and the payload doors. It's really nothing like a normal airplane. But anyway, back to entry. So if all went well, we should hit the first traces of the atmosphere at 400,000 feet and about 5,000 miles from our landing site. This is all good, but after a few minutes, there starts to be a little bit of a problem. We've got wings. And wings generate lift. And then, as we get into denser air, they generate so much lift that we're actually going to start to go back up and skip off the atmosphere. This is kind of bad. We really want to keep going down. So we could just pitch up. That would create more drag and less lift. But we risk overheating, overstressing, or just outright losing control of the orbiter. So we can't change our angle of attack, which means we can't change how much lift we generate. However, we can change which way it points. It doesn't have to point up. If we roll to the right or left, we can point our lift sideways instead of up. Well, this will effectively let us control how fast we're descending. With a steeper bank angle, we're going to generate less upward lift, so we're going to descend faster. Conversely, with a shallow bank angle, we're going to generate more upward lift, so we're not going to fall as fast. But that brings up an interesting question of how fast do we want to descend? Well, reentry is basically a big energy management problem. We have a lot of velocity and a lot of distance to cover. So the goal is to bleed off that velocity at just the right rate so that we cover the right distance. If we slow down too fast, we won't make it to the landing site. And if we don't slow down fast enough, we'll shoot right past the Kennedy Space Center and crash out in the Atlantic Ocean, which is also bad. So in order to control descent, we figured out that we just need to change our bank angle. But how do we control deceleration, how fast we're slowing down? Well, remember that the whole reason we're slowing down in the first place is because we're running into the air. So if we want to slow down faster, what we really need is more air. And where is there more air? Well, lower in the atmosphere. The atmosphere gets denser as you go down. So in a sense, we kind of already did figure out the right tools to control deceleration. Because if we bank heavier, that means we're going to descend faster, as we already know. So we're going to reach thick air faster. And the thick air is going to help us slow down faster. Conversely, if we bank shallower, then we're not going to descend as fast. So we're going to stay in the thin air longer, which means we're not going to slow down as fast. So there's just one last problem. We're kind of starting to turn. This bank angle thing isn't working out as well as we originally hoped. So NASA goes to its engineers and says, this is a really big problem. We can't just land in Panama. And the engineers say, we'll just turn the other way. This isn't rocket science. Why are you wasting our time, Steve? So, granted, this creates kind of this weavy S-turn reentry path, but it works. So before we go any further, let's review what we just learned. So we start with our deorbit burn, and that lasts for about 3 minutes. After that, we coast towards the atmosphere. While we do that, we pitch up to 40 degrees angle of attack, so our heat shield can protect us. Once we get into the atmosphere, we control everything with bank angle. If it looks like we're going to overshoot the runway, then we bank heavier so that we slow down faster. And if it looks like we're going to not make it, then we bank less so we don't slow down as fast. And also, every time we get turned too far away from our target, we just turn the other way in a series of what's called role reversals. That's what NASA calls it. This is the reentry, a picture of the reentry of STS-135, the last space shuttle. Something interesting about these reentry flames, that's not technically fire, although it kind of looks like it. It's essentially a really hot gas that's so hot that electrons break away from their atoms and molecules, and they start to glow this soft orange color. It's a different state of matter called plasma, which, even if you've never heard of it, you've seen it all the time in the form of neon signs, lightning. Most importantly, the sun is a big glowing ball of plasma. Now, as we slow down, we get less of this plasma, and we have less heat, so we're less concerned about melting. But we get more and more concerned with just falling out of the air. We really had to transition from spaceship to airplane. So at 8,000 miles an hour, we start bringing the nose down, lowering our angle of attack. Then at 1,700 miles an hour, we switch into a completely different guidance mode called Terminal Area Energy Management, or TAME. Now we're flying like an airplane, a really bad airplane. We have no engines, but we sort of function like an airplane. We pitch to control our descent rate, we bank to turn, and we've also got this speed brake thing that can open and close to help us control our airspeed. So also up to this point, we've been running on autopilot. an autopilot run by 5 of these redundant computers, each with a whole megabyte of memory. You couldn't even fit a single cell phone photo on one of these, but it was pretty good at flying the shuttle. But as we get towards the runway, the commander takes over manual flying, and this mode is called CSS, for Control Stick Steering, not cascading style sheets. Granted, the shuttle is fly-by-wire, which actually means that the computers run everything all the time. Even in CSS, it's really just the computer pretending to let the humans fly, just like normal life. Side note, no shuttle pilot wants to be called a co-pilot. That's just insulting. So in the left seat, we've got the commander, who does the flying. And in the right seat, we've got the pilot, not flying. I'm not totally convinced that NASA doesn't just do this to confuse the media, because it works really well. But back to Tame. So Tame actually flies us past the runway center line, and then around this imaginary spiral called the heading alignment cone. If all goes well, we should be lined up with the runway and on glide slope by 10,000 feet in altitude. Of course, if we were a typical airliner, on glide slope would mean a 3-degree descent path, flown at about 160 miles an hour, with a descent rate of about 750 feet per minute. But that's not going to work for us. The shuttle has stubby little wings and a big, fat, round nose. It's affectionately referred to as a flying brick. NASA astronauts train in a modified Gulfstream II jet, which, in order to simulate how unaerodynamic the shuttle is, flies with its landing gear down and its engines in reverse. So we're going to need a bit more brick-friendly glide slope of 20 degrees, flown at 345 miles an hour, with a descent rate over 10,000 feet per minute. To give you some context of how fast a descent rate that is, 10,000 feet per minute is about 120 miles an hour. That's terminal velocity for a skydiver in free fall. Now, obviously, we can't land like that. So at 2,000 feet, we start pitching up to bring the nose up in what's called a pre-flare maneuver. This trades the energy that we have in the form of airspeed in exchange for slowing our crazy descent rate. The landing gear comes down at 300 feet. We wait until this last minute because the gear creates a lot of drag, and once lowered in flight, it can't be raised again. We cross the runway just 26 feet, airspeed bleeding off like crazy. We touch down at 225 miles an hour. The drag chute is deployed, the nose gear is gradually lowered down. Just an hour and 5 minutes since we performed our deorbit burn, on the other side of the planet, we've landed the space shuttle. From space. Obviously. Where else would you land it? So, I want to leave you with what this looks like from the pilot's perspective. Because I'm a pilot, and I think this is the coolest thing ever. Of course, no one I've ever shown it to also agrees that it's the coolest thing ever, but I'm hoping Steve will. This is the night landing of STS-115. We are flying around the heading alignment cone right now. We're looking through the pilot's heads-up display. That's what all the green numbers passing by are. On the left, there is airspeed. We're somewhere between 260 and 270 knots. On the right is altitude. We're passing through 28,000 feet right now. In just a moment from the top, you're going to see the east coast of Florida come into view. It's the lights near south of the Kennedy Space Center. In the very center of the screen, there is a square with kind of a fuzzy diamond going in and out of that. That diamond represents guidance. So what the commander is trying to do right now is essentially fly that box over the diamond. And that will keep the shuttle on the right descent path and around the heading alignment cone. Also, that box is going to turn into a circle after a little bit. Doesn't matter too much. Well, it matters, but I don't want to explain it. At the bottom, which is now disappeared because the controls have been opened, apparently, there was a thing, it says CSS, and above that, It says HDG for heading. That's the heading alignment cone. And to the right, there's a horizontal line with a couple of triangles pointed at it. The top triangle represents the speed brake where it currently is right now. So it's open about maybe 70%. And the bottom triangle represents where the computer wants it to be, which is the same right now. You'll see that making adjustments as we go, and it'll make a big adjustment at 3,000 feet shortly before landing. There's a runway coming into view, and from 10,000 feet, I'm just going to let the astronauts talk for themselves, because I think it's a lot more interesting. The main voice that you're going to hear is the pilot talking to the commander through landing.
Brendan, 95 trail. There you go, 9,000. 2 and 2, look good. I agree. 8,000. A little bit of light crosswind on the deck. 7,000. Still good. I agree. 6,000. Okay, 5,000. My radar's good, and your radar's good. I agree. I'm going to decoder down, and I'm with you at just about 3,000. 3,000. Speed brakes. Speed brakes are moving to, looks like about 27. Okay. Hey, 2,000 pre-flare, the gear is armed. Copy, pre-flare. I see you in the pre-flare. I see you lagging a little bit. Looks good. 1,000. Max speed 313. 700. 600. 500. 400. Here comes the gear. Gear's moving. I show you coming down on the ball bar. You can turn your HUD up a little bit if you haven't. No, just a little bit high. I agree. A little bit high. There's 100 feet, 255. Plenty of energy. Corrected nicely. There's 50. I see the nose coming up. 3230. Okay, not too high, not too yet. There we go. We got 2210. You can start setting it down. There we go. 7, 6, 5, 4, 3. Touch. Here's the shoot. 0 second. And I'll show you going down at 1.5. Down at 1.5. Down at 1.5. Okay, touch.
So remember, there's no engines available, so this is their one and only chance at landing. I'd also like to point out that this video started about 3.5 minutes ago at 37,000 feet. That's a pretty typical cruising altitude for an airliner. So just think about the captain of your airline saying, ladies and gentlemen, we're beginning our initial descent into Philadelphia or whatever. We'll be on the ground shortly. And by shortly, he means 3.5 minutes. But that's the way that the shuttle flew, and that's it.